Hello, my name is Peter Allen. I'm a structural engineer with Nexsen. My colleagues and I are here to talk to you today about structural engineering. As an introduction, Nexsen is an architecture and engineering design company headquartered here in Virginia Beach. We have offices in Virginia, Georgia, and North Carolina, including right there in Raleigh. Our main work is the design of buildings, with projects throughout this region, as well as across the country and around the world. We have great teams of talented architects and engineers who work together to create some amazing buildings for all sorts of purposes: housing, education, recreation, healthcare, and many others. On the design team, structural engineers are responsible for the framework of the building, the internal skeleton that usually isn't visible in the finished product. But we know it's there, and we know the great responsibility that we have to make sure buildings are safe and long-lasting, long after our design work is complete. Virtually every building you see, every bridge you drive across, is there and functioning well because of structural engineers. You may recognize this building as Fitzwillard Hall at NC State. It's an architectural wonder, but it also has many visible features of engineering. And this is intentional. It's the main engineering building for the campus, so engineering students can see and experience firsthand the actual systems they're learning about. Now, we've talked about how important structural engineering is, but what exactly is it? In summary, it is the design and arrangement of materials and members to resist loads, to make something stand up against gravity, or the wind, or an earthquake. We determine what the skeleton and framework of a building needs to be in order to stand up to these forces. We use a variety of materials and a system of components to make this happen. We'll talk about each of those in more detail today. As you'd expect with engineering, there's a lot of math, science, and technology involved. We do a lot of calculations, drawing diagrams, and running computer analysis. We have to determine the forces on every structural element in the project and design it to safely resist those forces. Structural engineers are just one part of the design team that makes a complex building come to life. We work closely with architects, mechanical and electrical engineers, civil engineers, plumbing and fire protection engineers, each with their own specialty and adding their own expertise to the finished product. So teamwork is a very important skill. We also have to be familiar with construction methods and materials to balance strength, cost, durability, and appearance to create a frame that can be constructed in the time available, with the money available, and still support the architectural vision. Structural engineering involves investigating and discovering the numerous requirements and constraints of your project, and then working with your team to get the best possible solution. Structural engineering also has a creative, artistic side to it. Each building project is new and unique, with new problems that need creative solutions. We spend time sketching and visualizing various issues, exploring options, and developing alternative solutions. And once a problem is solved, we need to translate that math and science into pictures and drawings that can be used by contractors to construct the building. It's never boring and always challenging. One of the great things about this career is getting to see your design get built. Part of the work of a structural engineer is working with construction contractors to make sure that everything goes together correctly, that your design is properly executed. Seeing something you calculated and designed being built is really one of the most satisfying aspects of this profession.
Hi everyone, my name is Patrick Lakoff. I'm a structural engineer in training here at Nexsen. Today I'm going to talk to you guys about structural materials. Structural engineers consider all kinds of materials when designing a building. Most of the time, the material choice depends on what our client wants, what the architect wants, and what is required by the applicable building code. Cost of the materials is a key factor. Our client doesn't have all the money in the world to build the structure they want, so we have to keep that in mind when choosing the material we want for our design. Availability is important. Not all materials are available everywhere. For example, if you're in Alaska, you may not be able to get the same materials as you can in North Carolina. All materials are different, have different properties that are needed to be considered for us during design. One property is weight. We need to make sure that our building isn't too heavy because that will affect our foundation design. Another quality is strength. We want our materials to be efficient and be strong enough to resist all the loads that it's going to see. Durability is another quality that we design for. We want our structure to last long. We don't want it to be worn down by the environment or outside effects that impact the material. First, we're going to talk about concrete. Concrete is a material that we use very often as structural engineers. If you just sit and think about your everyday life, you see people walking on a sidewalk, driving on roads, the driveways of your homes. Typically, it's always some type of concrete. Concrete is everywhere. It can be used for any shape or size and for any need you have. Concrete itself is very strong in compression, but it's pretty weak in tension. Due to the weakness and tension of concrete, we add steel. Reinforcing steel is often called rebar, and this is what creates reinforced concrete. Reinforced concrete is also used everywhere. We use it in buildings, bridges, waterfront piers. Reinforced concrete is just a great material to use for design. Another material that we use is structural steel. Structural steel is very strong in tension, very strong in compression. It has all kinds of shapes that can be used for any need on the project. And that's why we like it so much. It's just very flexible for design purposes. We can use it to fit any need for any loading condition. Another positive of structural steel is that a lot of the connections that are made in the field can be done in the shop. You can do a lot of welding, pre-assemble everything essentially, and then when it's brought on site, it can be put together very quickly, which reduces labor costs, which reduces the cost of the project. And steel can be relatively lightweight if you compare it to concrete, and so it's pretty easy to transport and handle using cranes and whatnot. Another common material that structural engineers use is wood. Wood design is typically a specialty field of structural engineering that's used in residential construction. And as a material, wood is strong in compression, but it's pretty weak in tension, if you compare it to steel. And wood is a good option for materials when you're trying to reduce the carbon footprint of a building. We're in 2023, and there's a lot of goals as a structural engineering community to try to reduce the amount of carbon that goes into our design and building of structures. Concrete is very energy intensive to produce, and steel can be very energy intensive to produce, but wood typically is not very energy intensive, and it's very good for designing sustainable structures that can last a long time. Another material that we use is masonry, and masonry is a material that it's almost like Lego blocks. The blocks are stacked and connected with mortar. A lot of schools are built with masonry. If you look at your walls, there's a chance that those are masonry. Masonry can provide insulation for a building, which is great for reducing the cost of energy that is consumed throughout the life of the structure. Since it provides insulation, you're not going to get as cold or not get as hot as quickly. And we can add reinforcing steel to masonry to make it stronger to resist tensile loading. One of the downsides of masonry is that it's very heavy and labor intensive to build, and like concrete is also weak in tension. With all this information in mind, let's go over a brief summary. We're going to answer all of the questions and then go through them individually at the end. After our discussion, let's select which materials are strong in compression. You chose all the answer choices. You are correct. Next, we're going to talk about which materials are strong in tension. If you chose structural steel, you are correct. Next, which materials are considered lightweight? If you chose structural steel and wood, you are correct. We mentioned that concrete is great in compression, but not so great in tension. And this is why we add reinforcing steel to it. However, compared to steel, even reinforced concrete is not as strong in tension, and concrete is just very heavy compared to the other materials listed. As we talked about, structural steel is great in tension and compression and is a lighter weight choice than concrete and masonry, and still has all the design requirements that we need. Wood is strong in compression and okay in tension, but compared to structural steel, there's no contest. Wood is not as good in tension as structural steel. And wood is also a lightweight material. Then there's masonry. And masonry is great in compression, just like concrete. And also like concrete, it needs steel to be added to provide tensile strength, so it can be considered weak in tension. And masonry is also very heavy. All right, now that we're done talking about materials, let's talk about loads on structures. Loads are forces that structures experience during their lifespan that must be accounted for and designed. Structures must be strong enough and stiff enough to resist all of these design loads. As structural engineers, we determine loads based on the applicable building codes and design standards. The loads that are most critical in design are dead loads, live loads, wind loads, seismic loading, which is the loading caused by earthquakes, snow loading, and rain loading. Dead loads are loading a structure which stands that does not change throughout the life of the structure. For example, this photo shows a building under construction. There's no interior floors built yet. all you can see is really just the walls and the interior framing. So that's all dead loading. Now we're going to talk about other types of dead loading. Self-weight of the building, which I talked about, like walls and floors, but also the windows, the ceiling are all parts of the building that are considered dead load. Conduits and pipes for water, electrical, those are all considered dead loading. Air conditioning units on top of the structure, that's dead loading. And then floor coverings like carpet, hardwood are all considered dead loads. Next, we're going to talk about live loads. Live loads are loads that can be moved in a structure. Live loading is different than dead loading because live load may or may not be present, but it must be assumed that the live load will be there for us to design it. Now let's talk about types of live loads. For example, you sitting watching this video are considered a live load for design purposes. The chair and the desk you are sitting at are also considered live loads. Some other live loads that we design for are movable equipment, vehicles, stored equipment. Vehicles are a very critical design live load for roadways and bridges. Now we're going to talk about some of these photos that are shown on this slide. All these people crammed into one side of the office represent a live load of 96 pounds per square foot. Pounds per square foot is typically the unit that we use to account for loading. And for the sake of this discussion, we'll round up 96 to 100 pounds per square foot. 100 pounds per square foot is a very heavy live load. This is compared to normal design standards. For example, the ASU 7 design code states live loads for different buildings and rooms and whatnot. And live loading for a classroom is considered 40 pounds per square foot. So 100 pounds per square foot is almost 2.5 times the amount of the normal live loading in a classroom. Another common type of loading we consider is wind loading. Wind applies pressure to structures and causes them to move side to side. Wind on a structure is similar to how wind pushes a sailboat. The only difference is we want wind to push us when we're on a sailboat. We do not want wind to push a structure, so that's when design comes in. Design wind loading is typically done to account for wind loads that can be caused by hurricanes and tornadoes, as these high-level winds are not very common but can be crucial for the safety and stability of the structure. As you can see on this PowerPoint, there's an image from a ASU 7 design code that shows how wind acts on different sections of a building. Now we'll talk about seismic loads. As I mentioned before, seismic loads are caused by earthquakes, cause a building to move side to side, overturning. Seismic loading are critical for the design of structures on the west coast of the United States. And here on the East Coast, we still need to consider them, but they typically do not control our design. Snow loading is when snow piles up on a structure during a snowstorm. This is a critical load because typically if it's snowing, the temperature is below freezing and the snow does not want to melt right away. And if the snow doesn't melt right away, it can pile up very quickly. Obviously, snow is made of water and water is very heavy. So as this snow builds up, this can create a very large load on the structure, which needs to be accounted for in design. Rain loading is like snow loading, but rain typically does not accumulate as quickly due to evaporation and the fact that water moves a lot quicker than snow does. With some simple knowledge of loading in mind, we're going to see what you know with this poll question. Shown in this photo is some equipment hanging from the walls and ceiling of a building. What type of loading would you consider this photo to be showing? If you said dead load, you are correct. Pipes and conduit have a fixed weight and do not change throughout the life of a structure, which is why this is considered dead loading. This isn't live load because none of these conduits are removable, so you would not want to consider them as live load. Snow load is also incorrect because we are inside of a building and there's no snow present in the photo.
Now that you've heard about the different materials we build with and the types of loads we design for, let's talk a bit about some different types of structural members. My name is Alita Duff, and I'm a licensed structural engineer with Clark Nexsen. Structural members are like the puzzle pieces that fit together just right to help a structure resist the anticipated loading conditions. Different types of structural members include beams, columns, lateral framing, floor systems, and shallow and deep foundations. The first type of member we'll discuss are beams. A beam is a horizontal member that supports vertical loads, which we typically refer to as gravity loads. When these loads are applied, a beam will deflect downward in a bending motion. There are other loads that we design beams to support. Axial loads run horizontally and are typically applied at each end of a member. Axial loads either try to compress or stretch a member. Torsion is when a member is twisted along its length. Uplift is a different type of vertical loading where the beam is loaded from beneath and deflects upward in a bending motion. Beams can be made of several types of materials. Typically, if a beam is to be designed with steel, we'll use one of two shapes. Wide flange beams are shaped like the capital letter I with two horizontal flange plates and a vertical web plate. This shape is more lightweight and therefore cheaper than a solid rectangle of steel. Wide flange beams are typically used to support building floors and bridge decks. Another steel beam we use are steel joists. These look like trusses and are typically used to support roofs. Although these typically aren't as strong as most wide flange beams, because they're so lightweight, they can span much farther distances. Beams can also be constructed of concrete or wood. Another type of structural member are columns. Columns are vertical members that support vertical loads coming in from beams, floors, or roofs. They mainly support axial loads applied at either end of the member. Depending on how a structure is constructed, sometimes columns also experience bending from horizontal loads similar to beams. When a column is used to support both axial and bending forces, we call it a beam column. Columns loaded axially or in compression will deflect in one of two ways. If a column is relatively short for its size, it will crush or shrink. If the column is long, before it can be loaded enough to crush, it will buckle or deflect in a shape similar to how a beam would deflect. So where are columns used? As I mentioned previously, columns support loads coming in from beams, floors, or roofs. In the picture on the left, the load from the bridge deck is supported by horizontal bridge beams. These beams are supported at either end by a structure called a pier. Each of these piers are then supported by columns, which transfer the load down to the ground level. In the picture on the right, the floor loads from the building are supported by concrete slabs. These concrete slabs are then supported by concrete columns, which run down from floor to floor down to ground level. The previous two types of members we discussed are mainly used to resist vertical or gravity loads, but what about horizontal or lateral loads from wind or earthquakes? In the picture shown here, as the building tries to deflect or sway from side to side under lateral loading, the steel diagonal braces running between the floors are either compressed or stretched. The horizontal loads are then transferred to the columns, which eventually transfer the load down to ground level. Some other ways to laterally support a structure are with specially designed walls called shear walls, or with frames that have specially designed connections between the beams and columns called moment frames. Here are some examples of lateral framing. In the pictures on the left, these two buildings are being laterally braced with steel braces. However, in the pictures on the right, steel braces would run through the middle of the warehouses, so those aren't really an option. Instead, where the beams and columns intersect, they're connected rigidly with special connections that transfer the lateral loads through the structure down to the ground level. Rigid connections are typically more expensive, but need to be used in certain circumstances where braced frames aren't an option. So I keep mentioning how columns transfer the loading on a structure down to ground level, but what happens when the load reaches the ground? Structural engineers, with the help of geotechnical engineers, design foundation elements to transfer the loads from the building down into the soil. There are several types of foundation elements, such as shallow foundations and piles. Shallow foundations are typically constructed a few feet below ground level and are designed to spread out a force over a larger area. For downward forces supported by shallow foundations, think of how a snowshoe works. If you were to step into snow with just your boot, you would sink through. However, when you're wearing a snowshoe, the load is spread out over a greater area so that you can walk on top of the snow and be properly supported. Similarly, a shallow foundation will spread out the load coming down from a column or wall into a wide enough area so that the structural member won't sink in or settle into the ground. Sometimes when the soil is very weak or unstable, it's not feasible or possible to use the required size shallow footing the structure would need to be properly supported. In these situations, piles are used. Piles are like long columns that are embedded into the earth, and they can sometimes span lengths greater than 100 feet. These lengths depend on the findings of geotechnical engineers. They're embedded however deep is needed for them to reach stable, strong soil. Piles can be constructed of steel, concrete, or wood. Typically, piles are driven into the ground with a large hammer, but sometimes that isn't possible. In the picture shown here, these are auger cast piles. That means these piles were embedded by digging out the soil with a large auger. Then the hole was filled with reinforcing steel, and lastly, concrete was poured in to fill the hole. So now a poll question. This picture shows several of the members we've talked about, as well as an additional 2 or 3 that we mentioned but did not specifically go over. How many can you identify? As the arrows point out, this picture contains beams, columns, walls, lateral framing in the form of steel braces, and roof decking or slabs. Although not visible, there are also foundation elements below the ground supporting the structure.
A recent project of interest is the Virginia Beach Sports Center. Located near the oceanfront and resort area of Virginia Beach, it serves as an indoor athletic event center for the region. It features basketball and volleyball court space and a full indoor track, complete with adjustable banking and an infield for other track and field events. It's really amazing to see all this under one roof. The engineering for this project was challenging for several reasons. First, the building is located only about a mile from the Atlantic Ocean. As you know, the whole Atlantic coast is susceptible to hurricanes with high winds and flooding. So this building is right in the crosshairs of any major storm that comes up the coast. There was discussion during design about whether the city would use the building as an emergency shelter during these storms, which would have required us incorporating some extra safety factors and extra considerations into our design. While the city ultimately decided not to use it as a shelter, it is still designed robustly enough to weather the expected storms. As I mentioned before, doing local projects is great as we get to see them being built. At the Sports Center, we were able to see the foundation construction using reinforced concrete and shallow foundations. In these pictures, you see the workers placing concrete from delivery trucks. The reinforcing steel has been tied in place, and wood forms were constructed to form the concrete to the correct size and shape for the various foundation elements. Once the foundations are in place, it's time for the superstructure. The track and courts of the Sports Center required large areas of roof without internal columns. The result is the long frames you see here. The columns and beams are structural steel, which is perfect for this application, as it is strong and relatively lightweight. The scale of the structure is hard to see from these pictures, but this building is nearly 300 feet across and 50 feet high. The columns are up to 3 feet deep, and the roof girders are nearly 4 feet deep in places. Each frame was assembled in sections using multiple cranes and lifts. The segments were then bolted together to create the full frame. In the finished building, you can see how the long spans of the structure create these large open spaces for people to use and enjoy. You can see examples of the dead loads we talked about, the lights, ductwork, and athletic equipment suspended from the structure. All of these were discussed, planned, and evaluated by the engineering team during the design. One last special thing about the Sports Center, at least in our opinion, is that the structure is visible in the finished building. You can see the beams and columns quietly doing their job to allow this great space to exist. And if you're there as a structural engineer and your team is losing, at least you still have something exciting to look at. So, in conclusion, we hope that everyone learned a little about structural engineers and our work, and that you'll now have a solid foundation for your design project. If you have any questions, please lean on your structural engineering mentors or reach out to any of us. We're looking forward to seeing what you come up with and wish you well with your future studies.